Thank you, Professor Kim, for the introduction. Very happy to be here. And indeed, today I'd like to maybe also take a step back and look at what a lot of the time is actually invested on in the lab. So to start with, a small introduction of Zurich Instruments. So I'm a co-founder of Zurich Instruments. We started the company 13 years ago. Today we're about 140 people in a couple of countries. We have offices in China, America, Germany, Korea, France, Japan. Since last year, we're actually part of Rohde & Schwarz. That's kind of important because now, especially going towards the scale up, we actually have the possibility to involve large R&D power, for example, to develop ASICs. So this is something that we're now developing, the collaboration. Zurich Instruments will continue to exist as Zurich Instruments. It's our mission to take care of the quantum computing in the Rohde & Schwarz family. So our mission is to help build a quantum computer and be the leading supplier for quantum computing control systems. And we're doing so since about 2014, when we had our first setups for quantum computing. Then in 2018, we had our first complete quantum computing control system. That's what we call today Generation 1. That generation still required IQ mixing in order to reach the required frequencies. Now we're at Generation 2. It's a much higher integrated system, higher performance. It also generates the required frequencies right off the box. And the most recent addition is the ICQC, of which I will also show some measurements. And one thing that is also quite special about the ICQC is the way how it scales. So we see a scaling thrust where it's about making bigger quantum computers, improving the speed and the performance so that we can keep up with the many qubits. But we also have the technology thrust, where it's about improving the qubits. And this HHFQC, it works on both axes. Our software works on both axes, so that means researchers working on technology can readily transfer to the larger systems because the same instruments, same software, just in the largest, integrated in the larger system. So in this system, we integrate both control and readout channels, and we have a large bandwidth. We specify a gigahertz, but in practice you will see we actually use quite often 1.5 gigahertz, even up to 2 gigahertz. Of course, then you get a little bit of a drop-off. And one of the big advantages is that it's really very linear. So that is especially important when we are doing frequency multiplexing, and also a feature that you will see how it actually pans out. So some of the work we have been busy with is, for example, there was the 4 nanosecond gate shown by IBM, and that was the Stefan Philipp effort, where they, within 4 nanoseconds, could, in a very compressed waveform using optimal control methods, show the shortest qubit gates in the world. Error correction is always a big topic at Zurich Instruments. We're doing that on various different things. Here's a parity code that was shown. Then there's other efforts leading, what's that? Gate reflectometry, yeah, and most recently, and this is actually what I want to zoom in on a bit, is what we've done with ETH Zurich in the Wallraff group. So here we have a research project going on, actually two. It's the Open SuperQ and the American QSurf project, where we developed, where we're working towards the first logical qubit that is actually stabilized. And error correction is a challenging topic, not only because the error correction is a by itself already a complicated thing. You see it here. We have the ancilla qubits, we have the data qubits, and then again the ancilla qubits. We have the Z parity and the X parity. And so the ancilla qubits are read out. Then the syndrome is decoded. The ancilla qubits need a reset. That thing is repeated multiple times. In between the error correction cycles, actually the useful work is done. But in order for this to work, there's a lot of reality-induced problems that have to be overcome. So to get to the point where we can actually do the measurements, there's many months of work in order to get such a chip working. So here's a micrograph from the Wallraff group. And very thankful that we can actually see the chip. We don't see many chips of this size, so this is actually very nice that Andreas Wallraff decided to publish this photograph. And what you see here are the 17 qubits. You also see that there are qubits on the outsides, and then there's some qubits in the insides. You see there's a bunch of connectors, and this is already where the challenges start. For example, you see all the flux lines, that's the green lines. There are many of them, and each of them has a wire bond, and that's where we pick up the first crosstalk. Then it continues, the flux, it goes to those beautiful transmon qubits. But then we have also return currents. They also induce a magnetic field, which again we have to compensate. Then we see our control lines. To the outer qubits, that's pretty good. Going to the inside, you see this guy, for example, crossing two coupling lines, again crosstalk, something that we have to measure and then compensate for during the operation. So many months went into just characterizing the chip, figuring out how it works, what the problems are. And so there are many basic measurements that need to be done before we go into actually performing the qubit gates. So when we now get such a chip, the tune-up, how does it work? I want to walk you through a couple steps here. And what I will do is I will use the measurement results that we did when we first took our SHF-QC to try it out as a prototype on the system. And the measurements that I will show, they were taken within less than 1 day. It took about half an hour from the unboxing to actually get the first results, and that is because it's so nicely integrated. All measurements are done without any parametric amplifier. It's just a HEMT. So substantial averaging was required to get good signal-to-noise ratios. All qubit frequencies found within the second try. So that was really a big success story to see this come together. So the objective is perform the standard basic measurements, find the readout resonators, look at each readout resonator in detail, and then start with pulsed measurements. Starting out with a broadband measurement where we generate, where we have the readout line that reading is coupled to 5 qubits. And zoom in, and then the SHF-QC, the same box generated for all these 5 qubits, the control signals in order to do the qubit spectroscopy measurements. So to start with, we do a frequency sweep and we look for the readout resonators. There are 5 readout resonators. This is what the measurement looks like. Here you see a bit more than a gigahertz. I think it's about 1.2 gigahertz. So we usually try to pack our readout resonators into 1 gigahertz of spectrum. And what you see here is 1,000 points. Each point is integrated 10 milliseconds. The measurement, the theoretical limit is 1,000 times 10 milliseconds is about 10 seconds. the measurement takes 11 seconds. That's because the entire spectroscopy is done in hardware. It's not a software thing. And the FPGA executes all the entire spectroscopy very rapidly. And that's very important. If it's not done like that, a measurement that can take, in this case, 11 seconds, other setups quickly take, if it's going across software, many minutes, if not hours, to record such a spectrum. So what we see here are more than 5 absorption lines. We see 10. That's because each readout resonator has a Purcell filter, and they're quite close together, so we have a hybridization. So each qubit, 2 lines. There are 5 qubits. You also see that we get the phase information across the entire spectrum. You see that there's precisely, well, when we zoom in, we'll find a few more lines, but there are no artifacts from any, IQ calibration or drop-off at the sides of the spectrum. So how do we measure the qubits? We, as already introduced in the previous presentations, we do this dispersively. We have a detuning of the readout resonator that detunes according to the state of the qubit. So what happens is there's a resonator, here it's, and that in the ground, it's F-res, and then that shifts when the qubit is excited, and the difference in the amplitude, that's what we measure. That's the orange line here. So the orange line tells us whether to discriminate into the G or the E state. So now we need to sweep. Now we need to sweep the control frequencies, the control signals for all of these 5 qubits, and we do this in parallel. Now, if you have a chip with 17 or even more, 50, 100 qubits, to calibrate qubit by qubit is just taking too long. So what we do is we measure all 5 qubits at the same time. Again, it's done at the very close to the theoretical speed limit, 1,000 points, 20 millisecond integration each, so that's 20 seconds. The measurement takes 20.5 seconds, so there's half a second overhead for enabling channels and the triggering of the system. In this measurement, what we do is we create our 5 control signals simultaneously, and we take control, and we also read out all resonators simultaneously. So the readout signal is actually a an addition of 5 readout signals, and we sweep them in the same time. What you see here is, actually we can zoom into the first measurement a bit more detail. What you see is the main line. Here at this frequency, that's 6 gigahertz plus roughly 260 megahertz. There we hit the exciting frequency for the qubit. We also see that there's a spike here and there. I believe this one here is the crosstalk from the charge line. And this one here is the GF half excitation frequency. There are no other kind of spurious signals, even though we're driving all the other resonators at the same time, and that is we have very little intermodulation because of the really good linearity of the instrument. Good. Next step is once we have figured out where the qubits are in frequency step, we can start with our pulsed measurements. So that's typically the Rabi-Ramsey T1 measurements, and yeah. Again, here we can do this in a parallel manner. We don't go qubit by qubit, but we do it for multiple qubits or the entire chip in parallel. And that's really important again, because only if if this is very fast to do and easy to do, we can do it often. And that's really important to make this cheap. In order to do these measurements in an efficient method, we have to generate those pulse waveforms in an efficient manner. So we don't download flat waveforms. Instead, what we do is we use the sequencer and we use a parameterized generation of the waveform on the fly. What we supply the instrument with is the envelope. There can also be several envelopes. And what we can change in real time is the amplitude that the sequencer can change. That's programmatic. We can change the frequency that comes from a numerical oscillator. And we can also sweep the delay between the two pulses, not by having different waveforms, by using the sequencer. So this uses now very little memory, so the setup time is really fast, and again, the execution time is basically very, very close to the theoretical speed limit. Now, that's the one side, the very low end of bringing up a chip. I think it's frequently underestimated how much time actually goes into these steps, so we have gone into great length to make this as efficient as possible. On the system level, of course, now we have 17 qubits. We need multiple instruments. We need to connect them in the system, and this is where we have our PQC. We use a star topology, and for now, the star topology is just fine because up to 100, 200 qubits, this just scales well. Going beyond that, there will be multiple stars connected to each other, and they will reflect the code that is being used. Having scalable codes, that's what we anticipate for the future. We will mirror that in our system. So for each tile of the quantum error correction tile, we have a star topology to take care of that. All the sequencing is distributed in the instruments. That is one of the key features, properties of the architecture. And then we have a bunch of instruments that come in different variants with different channel counts, so that it's usually possible to get more or less exactly what the quantum hardware requires. So when we look at the quantum error correction experiment, it is a very particular layout. It's a very particular requirement it has. We have the requirement for rapid reset of the ancilla qubits. We have the requirement for global decoding of the syndromes, and then a global correction that is to be applied to the data qubits. And so for this particular setup, setup could look like this. We have our readout lines, they're multiplexed. So each readout line covers a couple of ancilla qubits and data qubits. We have some SHF-QCs, we have some HD-AWGs for the flux generation, and also some signal generators that generate additional control signals. So having the SHF-QC with a local feedback path, what we can do here is we can do a rapid reset of the ancilla qubits. So what we do is we connect all the ancilla qubits. It's drawn here just for one, but all the ancilla qubits of that particular readout line would be connected to the same instrument, so we can have a really, really fast active reset. Feedback time here is less than 300 nanoseconds. For the syndrome decoding, we need to take the bigger loop, because here we need global knowledge. We need to have in the FPGA the knowledge, the state of all qubits, and depending on that, distribute the feedback commands to all other instruments. This hop takes a bit more. Typically, it's about 500 to 1,000 nanoseconds. That depends a lot on how much computation for the syndrome decoding you want to do. Yeah. So then in the center, we have the PQC with the register bank. There are 32 registers. Each register is actually a quite big thing because each register contains up to 16 qubits, and we also track the history. So for the syndrome decoding steps, we can access the history of each register. That makes the programming quite easy because I can always write the readout into the same register. And then when I'm repeating, what's necessary often is to access the current plus the previous iteration. And a lot of these things work out of the box. I can set up, configure the system such that certain instruments always get the readout result of a particular qubit. But there's also a decoder unit that is very flexible. And here the customer can enter their own FPGA code. But also this is the place where other syndrome decoding technology can fit in. That can be GPUs, that can be ASICs, that can also be supercomputers. And that's something that we're working on with IQM. IQM is selling quantum computers, and they need to supply a 50-qubit machine by 2024. It will connect to a HPC, to a supercomputer, and it's our task at Zurich Instruments to make sure that that interconnection can happen both on the near time, like for rapid job execution, but also during coherence time. Because once we have the stabilized qubit, we will be able to run a lot of stuff during coherence time. We're definitely not there yet. In the example from the Wallraff group that I've shown, we need to improve the fidelities by about a factor of 2 to come below the error correction threshold. Yeah, the roadmap is there, and it's important that we start early with that because these interface definitions and developments, they always take a long time because a lot of alignment and communication with many parties is required. Good. So what are we working on today? Today, we have projects going on in Korea with SKSKU, Chris, Samsung. We're looking into helping and supporting as well as we can, make our little contribution to accelerate the progress as much as possible. It's obvious that the scaling thrust is a really important task, and here we are working quite intensively, both on hardware and on software. So there will be new hardware products coming too. Speed up as we go to larger systems is really important because something that is acceptable on a 10-qubit system, 20-qubit system, for 50 and 100-qubit system can already be no longer acceptable because measurements often don't just scale so well. So make all measurements, even in the bring up, parallel. That's like paramount. We have to parallelize these things. We can no longer afford to go qubit by qubit. And always in the back of the head, we have the idea of quantum error correction because we have to make the architecture choices so that once we have the system sizes and the fidelities so that we are sub-threshold, we can actually do that. It's important that the investment into the control system is sustainable, that our customers can use the instruments that they bought years ago still in the future. On the software side, there's a large team is just working on software. Here our idea is that we make sure that the basic measurements run at really high speed in a convenient way in a nice programming environment, but at the same time we are open both to Qiskit as a high-level interface so that from Qiskit we can directly execute the sequences on our instruments. We believe that's important for a couple of reasons. One reason is we can bring in more students into the lab, people that are used not only the experimental physicists, but also kind of more the theoretical people will be enabled to work with quantum computers that are actually controlled by Zurich Instruments. Also, openness towards other directions, for example, to Q control, so that we can add more value to the software stack is definitely what we're doing. Yeah, and always we will keep the access on the sample by sample level. That's really important, and the pulse level, and then finally also the on the gate level. So we have those 3 levels. All of them need to be there. If people want to work on a high level, then that must be possible. Good. With this, I'd like to thank you for your attention, and I conclude my presentation.
Thank you. Thank you for the nice talk. We can have a couple of questions. Yes.
Thank you, Sadik. Thank you, Sadik. Good talk. Just technical questions. So, I'm a chip maker, as I explained. So, chip design is really flexible, but the frequency is always decided by the RF electronics. So, 2 questions about frequencies. What's your decision reason for 8.5 gigahertz? Because I usually hungry for 9.5 gigahertz sometimes. If it's your business decision or cost decision, then forget about it. But if there is technical issue, then please explain. Again, the bandwidth of 1 gigahertz is a little bit small when you want to put many resonators there, because you need to separate them a couple of tens of megahertz usually. So please tell me about those bandwidths and frequencies, number 1. Number 2 is the latency. You have something like 300 nano to 500 nanosecond latency. That's, I think, still pretty slow. So do you have any idea to get it, let's say, 100 nanosecond in the end?
Yeah, that's a wonderful customer question. They always ask for more. So to start, why 8.5 gigahertz? There are actually technical reasons why it's a compromise. If it was really easy to go to higher frequencies, we would have done that. In the scheme that we have chosen, it's this double superheterodyne. It is the availability of certain components that permitted us to go to 8.5 gigahertz at really high signal performance. And if we want to go beyond that, we have to go into a kind of different family of devices, but they don't perform so well. So what we do here is we are now working, actually we already have that, on a way how to extend up to 14 gigahertz. So with some external electronics, you can now extend from 8.5 to 14 gigahertz. And that will take care of some of the outliers. Usually, we find, though, that 8.5 gigahertz are sufficient. So we don't intend to now make a new instrument that will go to higher frequency. Then the bandwidth question, you say 1 gigahertz is a bit tight. So we specify 1 gigahertz quite rigorously. And even in the measurements I've shown, I think they went up to, not sure, 1.2 or 1.4 gigahertz. So in practice, I think it's totally fine to operate at least until like 1.4, 1.5 gigahertz instantaneous bandwidth. If you go beyond that, you will start suffering from cutoff. The high bandwidth is primarily required for the readout. And here's the question, how many qubits are sensible to actually multiplex? And from discussions, we believe that the sweet spot is somewhere between 5 and 9, maybe around 7. And the reason for that is the more multiplexing you do, the sooner you run into compression on the amplifiers of the readout stage, and you're going into a regime of diminishing returns, because whether you have 7 or 10 qubits per readout line, it doesn't save many inputs. So With the bandwidth, as we showed, we don't see limitations really in practice. But you're right, if 1 gigahertz was a hard limit, then yeah, that could be tough. What was the last point? Latency. So we are actually quite happy with the global feedback latency. And here the point is that that is very quickly dominated by the syndrome decoding. For the active qubit reset, the fast one, smaller than 300 nanoseconds, I think we still have a little bit of air that we can squeeze out, but ultimately we are also running here into the limitations that are given by our employed ADCs and DUCs. So yes, there could be some more improvement, but it's not going to be 100 nanoseconds. And the reason for that is that the devices that we use for ADCs and DACs, they just don't permit for that.